Alright, what's up guys? It's Professor B and I'm back today with another physics problem. We're going to be doing centripetal acceleration today. And for those of you that don't know, in Latin, centripetal means towards the center. So a little bit of concept before we start. Let's say we have a ball going around the circle. This ball is experiencing what we call uniform circular motion. And the force acting on it, it's towards the center. Like if you're in a merry-go-round, the force that you feel that wants to throw you off is what we call a pseudo force. It's not a real force. The only force that's real is the one that's pointing towards the center. So if we let the center equal r equals 0, then the further away we get from r, it's going to be in the positive direction. And the closer we get to r is going to be in the negative direction. So the further away we get from r, the bigger r gets. And the closer we get to the center, then the smaller that r gets. So let's go ahead and jump straight to the problem. It says a 40-kilogram child swings in a swing supported by two chains, each 3 meters long. The tension in each chain at the lowest point is 350 newtons. They want us to find the speed of the child at the lowest point and the force exerted by the seat on the child at the lowest point. So we have our child in a swing. And they want us to ignore the mass of the seat as well. So each of these chains, we can call it T. And we know that T is equal to 350 newtons. We know the mass of the child is 40 kilograms. And we know that the length of each chain is 3 meters, which we can call R is equal to 3 meters. And I'll explain why in just a second. So let's say that this dot is the child. Then the two forces that the child is experiencing, because remember the child is swinging back and forth, back and forth, back and forth. So we can draw a half circle. And the force, it's towards the center, which we can call the tension. And the other force, the only force that we are going to show, because we are ignoring the mass of the seat, is going to be the force exerted by the child's weight downward, which we can call F of G. So because we are ignoring the mass of the seat, we don't have to show a gravitational force pulling down on the seat itself. We are only showing the gravitational force that is exerted by the child's weight downward. So because our R is the center of the circle, then that means that the tension is negative. So T of R is going to be negative T. And because our gravitational force is away from the center, then it's going to be positive. So F of GR is equal to the magnitude of F of G. The truth of the matter is, guys, we know that we have a coordinate axis labeled as X and Y. The only difference is that we are, instead of X, we are calling X R. So think about that. We're letting X be R, and we're analyzing the centripetal acceleration for the radial component. Now, using Newton's second law, we know that F of net R is equal to the sum of all the forces. Should put the sum right there of all the forces, which is going to be negative T plus the gravitational force. It's probably unnecessary, but you get the idea. Now, we know that F of net R is equal to MA sub R. And if we plug in for A sub R, we have negative V squared over R. Our A sub R is our radial component going towards the center. And again, because it's going towards the center, it's in the negative direction. That's why we put a negative. Now, plug in this into here. We will have negative m, the magnitude of v squared r is equal to negative t plus f of g. So they want us to find the speed of the child at the lowest point. So we would simply just need to solve for v. So if we multiply both sides by r and divide by m and multiply by the negative, then we would have v squared is equal to r times the tension minus mg, which is the gravitational force. F of g is equal to mg divided by m. Taking the square root of both sides, that is our final equation. And plugging our numbers in, we would have our radius, which is the length of the rope, which is 3 meters, times the tension, which is 350, minus the mass, which is 40 kilograms, times gravity, which is 9.8. All over the mass, again, which is 40. And we take the square root of that. Now, because T is equal to the tension of one of the chains, we need to take into account both of the chains. So we would have to multiply this by 2. And putting that into your calculator, we would have 2 times 350 minus 40 times 9.8 all over 40. We would have 4.8062 meters per second. And that is the velocity of the child at the lowest point. Now we want to find the force exerted by the seat on the child at the lowest point. So because the child is sitting on the seat, right? The child is sitting on the seat is exerting an upward force on the child, which is the normal force. So this would be F of n. And again, we have our gravitational force, F of g. So our F of n, because it's pointing towards the center of the circle, remember the child is swinging, and the motion of the swing is creating a half a circle. So that is how we can apply that to the centripetal acceleration. So our Fn, our component, is going to be negative F of n. And again, our F gravitational force is going to be positive F of g. So if we sum up all the forces using Newton's second law, we have F net of r is equal to the negative normal force plus F of g. Now let's go to the side, and we know that F net of r is equal to MAR, and we know what AR is, so if we just plug in negative v squared over r, remember it's the magnitude, because A of r is our radial component that's pointing towards the center. So therefore it's negative. So plugging everything in, we can plug this into here, and we would have negative m, the magnitude of v squared, all over F of g minus F of n. So they want us to find the force exerted by the seat on the child at the lowest point, which is the normal force. So we just solve for the normal force. So F of n is equal to mg, remember that, the gravitational force is equal to mg, plus mv squared over r. And this would simply be F of n, plugging our numbers in, we know that it's 40 times 9.8 plus 40. And the velocity, I believe it was 4.8062 squared all over the radius, which is 3 meters, which is the length of each chain. Plugging that into your calculator, you should get, I believe, would be 700. Let me just double check. Plus we have 40 times 4.8062 squared divided by 3. And to be exact, you'd get 699.9941 newtons, which rounds up to 700 newtons.